Welcome to this, the first lesson on acids and bases, and it covers the start of the specification reference 3.4.3. What we're going to learn in this video lesson is as follows. Firstly, we're going to know that an acid is a proton donor, whereas a base is a proton acceptor. Previously, you've understood acids to involve H+ ions, and alkalis, bases, to involve hydroxide, OH- ions. But this is a new concept of proton donors and proton acceptors. So we're also going to know by the end of the lesson that acid-base equilibria, that's just equilibrium reactions involving an acid and a base, and they involve the transfer of protons, which you might at first glance think that's quite confusing because protons have got to come out of a nucleus, and how can we transfer those without nuclear reactions? Okay, we will understand that by the end of the lesson. We will also know that weak acids and weak bases dissociate only slightly in aqueous solution. And water is weakly dissociated. We are going to understand that the water that we get out of a tap is not just H2O molecules, it's also H+ ions and OH- ions as well. We're going to understand that. And lastly, we're going to understand the following expression. We're going to understand that Kw, another K, is equal to the hydrogen ion concentration times the hydroxide ion concentration. More on that later. Okay, you may not have known it, but the definition of acids and bases that you've been working at so far is called the Arrhenius definition. But here we have Bronsted-Lowrey as a different definition of acids and bases. Bronsted and Lowrey were two chemists of yesteryear, and what they said about acids and bases is that a Bronsted-Lowrey acid is a proton donor. So let's have a look at a generic acidic reaction. So let's say we've got HA, where A could be anything, but H of course is hydrogen. All right, and that's in aqueous solution, and that's going to be in equilibrium with the dissociated parts of that molecule, which are the hydrogen ion, also known as a proton, and the conjugate base. So the conjugate base has taken the hydrogen's electron to leave it with a negative charge, and the hydrogen atom without that electron is a hydrogen ion or a proton. And so the acid is actually this part of the equation. This is the acid, and what it has done in this dissociation is donated the proton, and that's what makes it an acid according to Bronsted-Lowrey. Now in an opposite fashion, we can look at Bronsted-Lowrey bases, and they do the opposite. They are proton acceptors. So looking again at a generic equation, let's say we have a base, all right, and that's going to be in water. And that is also in equilibrium, but the base has accepted the hydrogen ion from the dissociated water molecule, and when that dissociated water molecule gives up its hydrogen ion, what's left is a hydroxide ion. They are both aqueous. So this is the base, and what it has done in this equilibrium reaction, it has accepted that proton there. It has accepted that proton, and that's what makes it a base according to the Bronsted-Lowrey definition of acids and bases. Just one last point on this. These hydrogen ions that we have in the acid equation are just protons, and protons are very reactive. They don't just hang around on their own. What they do in aqueous solution is they hitch a ride on a water molecule. And so if you had a hydrogen ion and a water molecule, that would, well, let's draw it as an equilibrium reaction. That would form the hydroxonium ion, H3O+, and that's actually how it exists in reality. But as far as the exam is concerned, you can write hydrogen ions and you won't be penalised. They will also accept hydroxonium ions with the same regard. Okay, this part of the lesson is on dissociation of either acids or bases in water. So the acid molecule or the base molecule, when it dissolves in water, how much does it dissociate? First of all, let's just make sure we know what the word dissociation means, and that is another word in this context for breaking up. Let's consider first strong acids and strong bases. Alright, so strong acids or bases. And the fact of the matter is that they dissociate completely. They dissociate completely, all right, and let's just show you what that means. Let's take a strong acid, for example, HCl. All right, so as a gas, the acid molecule is HCl, and then when it dissolves in water, so let's say as a gas, and then it dissolves in water, and what you get is that covalent bond breaking up, and the hydrogen ion exists on its own separately from the chloride ion when they are in water. So let's write that as aqueous and aqueous. And that happens completely. So this bond that exists between the hydrogen and the chlorine atoms in that molecule has dissociated, right? And all of the molecules of hydrogen chloride do this, and that's so that we call that fully dissociated, and that's what makes it a strong acid. Let's use sodium hydroxide as an example for a base dissociating completely. So sodium hydroxide would exist as a solid before it's dissolved in water, and when it is dissolved in water, then you would get a sodium ion and a hydroxide ion, both aqueous as they're dissolved in water, and they would dissociate completely. So all the ionic bonds that exist in the lattice between sodium ions and hydroxide ions, all of them are broken, and so none of the solid remains as lattice once it's dissolved in water, and all of the ions are freely dissociated, swimming around attached to various water molecules. So that's what we mean by strong acids and bases. Now let's consider weak acids and bases. So weak acids and bases are those that dissociate only slightly. Dissociate slightly, whereas strong acids dissociated completely. So let's have an example of a weak acid. Let's take ethanoic acid. So we would have, and I'll draw the displayed diagram of ethanoic acid. So you've got CH3 and you've got COOH as the displayed formula, and that is in equilibrium once it's dissolved with the CH3 CO- ion, and also the hydrogen ion that has dissociated off is there as well. So this here is the bond that dissociates, the one between the oxygen and the hydrogen. And when it does, the oxygen keeps that hydrogen's electron there, leaving the conjugate base with a negative charge. And here we've got the hydrogen ion that's left in solution. Now, when we say dissociate slightly, what we mean is the bond that dissociates doesn't always dissociate. You've got lots of these molecules, the whole molecule there, that stay as they are, and only some of them lose their hydrogen ion, and that's why we say it's only dissociated slightly. Okay, looking at an example of a weak base, let's use ammonia, NH3. So when NH3 dissolves in water, we have an equilibrium reaction set up such that the ammonia forces the dissociation of this water molecule such that it accepts a proton, right, to become, so it was NH3, it would accept the proton, so it's got 4 hydrogens and a positive charge because the hydrogen ion didn't come with any electrons, just its own positive charge. And of course what it leaves behind is the OH minus ion, and these of course are both aqueous. Right, and in the same way we are talking about dissociation, and so it's this bond here that dissociates to leave a hydrogen ion and OH minus ion, and that hydrogen ion attaches itself to the ammonia to make the ammonium ion, which has the ammonia has accepted the proton, the hydrogen ion, in that basic reaction. But that bond breaking, that bond dissociation, only happens to a very small number of water molecules, and so this equilibrium is far over to the left. So before we just did dissociation in water of either acids or bases, what we're going to do now is look at how acids and bases react together. And we're going to name, of the components of a reaction, we're going to name which ones are acids and which ones are bases according to the Bronsted-Lowrey definition. So let's have a look at a generic acid-base reaction. Okay, so we'll start with HA, where H is hydrogen, but A could be any conjugate base. So we've got HA, and that's going to be in solution, and let's say the base is actually water. Right, so you've got the acid reacting with the water. It's an equilibrium reaction because we've got 2 reactions going on at the same time. And what we see is that this is the bond that dissociates, and you get that hydrogen ion leaving without its electron. So it's an H plus ion. So it turns into a H plus ion, and it reacts with this water molecule to make a hydroxonium ion. And of course that's left A, so A has kept the electron, so that turns into A minus, and A minus floats around on its own for now. Like that in solution. So what we can say, therefore, is that in this forward reaction, let's deal first with the forward reaction. The acid is the particle that has donated the proton, right? So HA was the acid, and water was the molecule that accepted the proton, right? So that was the base. And while we're at it, let's choose purple and consider the backward reaction. Now the backward reaction, we have as our reactants the hydroxonium ion and the A minus conjugate base, and the hydroxonium ion is losing its proton. So this proton from one of the hydrogens is lost, and so that is losing or donating a proton. So that is the acid. And where is that proton going? Well, it's going to be attracted to the negative charge on this conjugate base, and that conjugate base is going to accept that hydrogen, and so that is the base when we consider the backward reaction. The last little concept that we need to get our heads around in this lesson is called the ionic product of water, and it's only to do with water, and it has the symbol Kw. Unfortunately, a third K for us in recent lessons, but there it is. This is the ionic product of water, Kw. So let's start off by considering what happens in water. So if we look at two water molecules, you've got H2O as a liquid, and you've got another H2O molecule as a liquid, and as they exist in reality, the odd time one of these water molecules dissociates, right, and this hydrogen ion joins up with this water molecule, and this OH minus ion floats off on its own. And so what you get is a H3O plus hydroxonium ion in aqueous solution, and a hydroxide ion also in aqueous solution. And we can actually simplify this too by taking a water molecule from both sides, and that just means that the water molecule is in equilibrium with its hydrogen ion and hydroxide ion as they dissociate. So although in water this only happens to a tiny extent, such that the equilibrium is well over to the left-hand side, the water side, nevertheless it is an equilibrium reaction, and if so, we can write the equilibrium expression for it. Alright, so going back to the previous equilibrium constant, not the ionic product one that is in the title of this. So you'll remember that the equilibrium constant is the concentrations of the products times their molar amounts from the balanced equation divided by the concentration of the reactants in the equilibrium equation, which in this case is water. So we have a equilibrium constant expression here for water as it dissociates slightly. Now, as we've said, the equilibrium exists way over to the left-hand side. So what we can say is that this concentration of water is pretty constant, right? To all intents and purposes, it is constant. And if it is constant, and also by definition, the equilibrium constant is constant at a given temperature, we can multiply a constant by a constant and get a constant. Okay, so let's just do that in black. Alright, so if we start off with our equilibrium constant and multiply it by the concentration of water in this situation, which we're saying is effectively constant, we can say that that is equal to, right, and we're going to call that the ionic product of water. And as feeding the values into the equilibrium expression, that's going to be the remaining terms on the numerator, so that's the H plus concentration times the OH minus concentration. So that is the expression for the ionic product of water. Kw, the ionic product of water, is the hydrogen ion concentration times the hydroxide ion concentration. And that's going to be true at any particular temperature. If you change the temperature, you're actually going to change the amount of dissociation in the water molecules, and so the ionic product will change. But that's constant at a constant temperature. As it happens, we can simplify that one step further, because in a water molecule, you're going to have it dissociate into one hydrogen ion and one hydroxide ion. So the concentrations of the hydrogen ion and the hydroxide ions are going to be the same. So we can also write this as the ionic product of water is equal to the hydrogen ion concentration squared. So that's an alternative expression for the ionic product of water when we are considering pure water. So hopefully now we know the following. We know that an acid is a proton donor, whereas a base is a proton acceptor, where those protons are actually hydrogen atoms that have lost their electrons. And we also know that acid-base equilibria involve the transfer of protons, not from the nucleus, as we mentioned right at the start, but those protons are just hydrogen atoms that have lost their electrons. We also know now that weak acids and weak bases are those that only dissociate slightly in aqueous solution. And we also know that water is weakly dissociated. It dissociates into hydrogen ion and OH- ion. And we've also derived an expression, which we can write down again. We've derived an expression for the ionic product of water. So the ionic product of water is the hydrogen concentration times the hydroxide ion concentration, and for pure water is also equal to the hydrogen ion concentration squared, because these two are the same. Thanks for listening. I'll see you on the next video.